Welcome to The Explainer. Today we're going to solve a fascinating little mystery from the world of materials science, and it's one that might just be happening on a shelf in your own home right now.
So let's start with the central puzzle. Picture this. You've got a cool old die-cast car or some metal figurine. It seems perfectly solid, but then, years later, you look at it and it's covered in these weird cracks and blisters. It's literally falling apart from the inside. So what is going on here?
Well, the first thing to know is, this is not rust. We all know what rust looks like, that reddish-brown stuff on iron. No, this is something way more sneaky. It's a process called zinc pest, and it attacks the metal's very structure, from the inside.
And this quote? This really nails it. This is the core idea we're going to unpack. It perfectly captures the problem. The metal object itself contains all the ingredients to become its own battery, a battery that's powering its own doom.
So, how in the world does a piece of metal just self-destruct? Let's dive in. First, we need to understand exactly what this thing is, and maybe, just as important, what it isn't.
Right, so the key thing here is that zinc pest isn't like a surface scratch or a little tarnish you can just polish off. It's an electrochemical process. That means it involves both chemistry and a tiny bit of electricity, and it all kicks off deep inside the metal on a microscopic scale.
All right, let's go to the scene of the crime and see how this all gets started. To really get it, we need to zoom in, way, way in, into this hidden world of metal crystals.
You see, most metals, and definitely the zinc used in old die-cast toys, they aren't one big solid piece. They're what's called a polycrystalline solid. Now that's just a fancy term that means they're made up of millions of teeny-tiny individual crystals, or grains, all jammed together like a microscopic mosaic.
Now, where all these millions of tiny grains bump up against each other, you get these dividing lines. We call them grain boundaries. You can think of them like the grout between tiles. The problem is, the atomic bonds here are weaker, which makes these boundaries the perfect, chemically vulnerable spot for a bad reaction to start.
Okay, so now we know where this all goes down. The next question is, who are the culprits? Who's responsible for kicking off this whole destructive chain reaction?
Well, our main suspects, the real instigators in this materials mystery, are tiny, tiny amounts of lead and cadmium. These are basically impurities that were often left over in older zinc alloys from the way they were made.
And here's how they lay their trap. When the hot, molten zinc alloy starts to cool down and get solid, the zinc crystals form first. But lead and cadmium, they don't really dissolve into solid zinc. So as the zinc solidifies, these impurities get pushed aside, shoved right into those weak grain boundaries we just talked about. They end up getting super concentrated in the absolute worst places. And this is where it gets really wild. So we've got our location, the grain boundaries, and we've got our culprits, the impurities. Now let's see how they team up to create a weapon of self-destruction. What happens is, having these pure zinc grains right next to these lead-rich boundaries creates the perfect setup for something called a galvanic cell. And a galvanic cell is, for all intents and purposes, a tiny battery. The metal literally has millions of microscopic batteries embedded all through it.
This is just a recipe for disaster. In each of these little batteries, the zinc grains act as the negative terminal, the anode. They are the sacrificial metal. And the lead impurities, they act as the positive terminal, the cathode, driving the whole reaction. The zinc is literally sacrificing itself to the lead.
So this four-step process is basically the engine of destruction. First, the zinc atoms dissolve and release electrons. Second, those electrons flow over to the lead. Third, add a little bit of moisture from the air, and a reaction kicks off at the lead. And fourth, this whole thing creates new corrosion products, all happening deep, deep inside the metal. So, what happens when you have millions of these tiny batteries running nonstop, day after day, year after year, inside the metal? Well, the result is predictable, and sad to say, it is totally irreversible. What makes this so incredibly destructive is that it's a self-reinforcing feedback loop. Once this thing gets going, it only gets faster and faster, because the damage actually feeds the process.
Remember those corrosion products that get formed? Well, they physically take up more space than the original zinc did. This expansion creates this huge pressure from the inside, literally pushing the metal grains apart. That creates tiny cracks, which then let in more moisture and oxygen, which speeds up the battery's reaction even more. You see the loop? And that explains the whole time bomb effect.
This process can be incredibly slow at first, just silently incubating for decades. An object can look absolutely perfect for, say, 40 years and then, boom. Once the internal damage hits a tipping point, it suddenly starts to crack and warp and crumble.
And here's the real takeaway. Once this starts, you can't stop it. You can't reverse it. Sure, you can slow it down by keeping the object in a super dry place, but the tragic reality for a collector is that the internal structure is permanently broken. Those tiny batteries are built right in, and you just can't take them out.
So, let's zoom out and put this all in context. Why does this matter? Well, it reveals something really fascinating about the dual nature of zinc itself.
Check this out. You can really see the two faces of zinc here. With Zinc Pest, it's the structure and the sacrificial part, so it corrodes from the inside out and destroys itself. But then you have galvanized steel, where we intentionally coat steel with zinc. There, the zinc acts as a sacrificial shield on the outside to protect the steel underneath. It's the same element, using the same electrochemical principle, but with one huge design difference that leads to protection instead of destruction.
And this all has some very real-world consequences. For anyone who collects old Diecast toys, for example, it means that if an item was made with one of these impure alloys, its eventual failure is a scientific certainty. Even keeping it sealed in the original box can't stop that internal chemistry forever.
It really makes you think, doesn't it? When we look around at all the everyday objects we just assume are permanent and stable, what other slow, invisible processes might be at work, silently ticking away deep inside the materials themselves?